Hi, everyone. Starting from today, for the next couple of hours, I'm going to talk about sensitivity analysis, which helps in determining the sensitiveness of the optimal solution in the context of changes in the parameter values or data values in your LP model. Okay, so let me share my screen. Okay, is it? So earlier this semester, we've talked about a few assumptions for a linear programming model. One of them is the certainty assumptions. And one of the major challenges encountered by most engineering and business enterprises is we cannot be sure of the data the parameter values that we put into the LP model. So what if a situation turns out to be different compared to the key predictions you made already? Of course, you cannot just sit back and doing nothing, right? You have to revise and update your LP model. So it's very important to find out the robustness of the optimal solution to the uncertainty data. So the major goal of the sensitivity analysis is to know how changes in the data values, parameter values in your model affect on the optimal decision. Okay. Okay, so more specifically, we are going to talk about how changes in a coefficient of the objective function affect the optimal solution and how changes in the right-hand side values of each constraint in your LP model affect on the optimal solutions. So basically, if a parameter data changes, then knowledge of sensitivity analysis enables us to determine from the optimal solution, original solution, how changes in an LPS parameters change its optimal solution without solving the problem again, okay? So that's why sensitivity analysis is very important. Okay, so to illustrate the basic concepts of sensitivity analysis graphically, let's reconsider window glass example that we discussed earlier this semester. So in this example, window glass makes two glass products, right? Door glass, a glass door, and windows in three different plants. And there is a different time requirements for producing these two products in each plant. And each plant also has different capacity. So that results in different time schedule in each plant, right? And all the information been summarized in this table, and you are required to provide a production plan that will maximize the profits of window glass company, okay? Okay, so because you have to decide how many doors and windows has to be produced each week to maximize the total profit. So we define two decision variables, x1 and x2. Each stands for number of the batches of doors and windows produced per week, right? And our goal is to maximize the weekly profit from producing these two products. And so basically in this LP model, we considered a resource constraint for each plant, right? So in each plant, there is a different amount of labor hours required for producing the two products, and the capacity of each plant is also different each other. And of course, the production rate cannot be negative, so we added a non-negativity restriction to each decision variables, right? Okay, so putting all together, this is the complete LP model for window glass example problem. So now let's put this LP model in Lindo or Lingo, so that we can use the Lingo or Lindo output later today. So, okay, open up Lingo. Okay. So this is the Lingo window, right? And so I'm gonna use Lingo input. Okay, I'm gonna copy all of this. Put them in here. Let me just disable my camera. Okay. So Lingo does need equal sign, right? Right after max or min. And we need asterisk as the multiplication symbol. And we need a semicolon indicating the end of objective function. We don't need st or subject to. And we need to change it to less than equal sign, right? And then semicolon. In front of comments, we put the exclamation mark. And also the comments will be ended with semicolon. And we'll do the same thing for the rest of constraint sets. So asterisk symbol is less than equal sign and semicolon, exclamation mark and semicolon, like that. And the plant number 3 constraint is that. Less than equal sign. And we don't need to specify non-negativity constraint because both Lingo assumes all of the decision variable used in the model, so non-negative real values. Okay. That's it. So if you run it, we receive the optimal solution right away. So according to the Lingo output, to maximize the total weekly profit, the window glass has to produce 2 doors and 6 windows weekly, right? In a way, they can maximize the weekly profit, which would be $36, okay? Or $36,000. Okay, so that's the Lingo output. And we will be back this output value later today. Okay, so now let's get back to our PowerPoint slides. Oh, and one more thing. So, okay, let me maximize the window. Okay, so this is the Lingo output, right? It does provide you the optimal objective function value and the optimal solution. Those are x1 and x2 value, right? And also it provides reduced cost for each decision variable and the dual price for each constraint, okay? And also it provides slack variable or surplus variables. So we are going to talk about this very soon. And also let you know, Lingo and also Lindo provides additional information that can be used for sensitivity analysis. So what you need to do is before you run Lindo and Lingo, go to Solve menu and then choose option. And then under the General Solver tab, okay. So under the General Solver tab, in the dual computation box, select prices and ranges option, okay? And then because I already did it earlier, so it doesn't show, but in your case, if you didn't do this earlier, then after you choose this option, prices and ranges option, make sure you press apply button and save, okay. And then after that, what you need is just run it, run the program, then you're gonna get the optimal solution, right? And then get back to the model screen. And what you need is go to solve, and then this time choose range, okay? Then you're gonna get this prices and ranges information, okay? And we are going to talk about it in a minute, okay? So let's go back to our screen. The PowerPoint slides. Okay, so that's what I've told you. Okay, so earlier we learned how to find the optimal solution using the graphical method, right? So let's revisit the graphical method for the window glass example. Um, so here the blue area is the feasible reason of window glass problem, right? And the okay, so having identified the feasible reason, now we can search for the optimal point. So we draw an isovalue line last time, right? Do you remember? So to draw the isovalue line, what you need is to choose any point in the feasible region and calculate its optimal, its objective function value, right? So for example, okay, if you choose 0.02, then the corresponding objective function value becomes 10. So 0.2 lies on the isovalue line, which is 3x1 plus 5x2 equals 10, right? And rewriting this as x2 equals negative 3/5 times x1 plus 2, right? So this line has a slope of negative 3/5 and x2 intercept of x2 intercept of 2, right? The thing is, every isovalue lines have the same slope. So once we have drawn one isovalue line, then we can draw all the other isovalue lines, right? What you need is just moving parallel to the isovalue line you have drawn, right? And in this problem, the objective function value will be increased if we move the isovalue line in this direction, right? So in a way, both x1 and x2 values will be increased, right? And we know that the optimal value of 36 could be found with the isovalue line that intersecting or touching the feasible region, right? So that's going to be the last isovalue line, right? So we know that the optimal point occurs right here. Okay. Now we are ready for the graphical explanation of the sensitivity analysis. So let's suppose we'd like to know the effect of a change in the objective function coefficient on the optimal solution, okay? So in other words, we'd like to know the effect of a change in the slope of the objective function line on the current optimal solution. So, for example, if I change one of the objective function coefficient value here from, let's say, 3 to 10, for example, then what's going to happen? In that case, this value will be changed to 10, right? So obviously the slope of the isovalue line will be changed, right? Okay, so here, let's call this C1 is the objective coefficient value for variable x1. So basically C1 is the contribution to the profit, total profit by each door, right? Okay, then the question is how much we can change C1 without changing the current optimal solution, okay? So in other words, I want to see for what ranges of C1 values the current basis remains optimal, okay? So currently the C1 is 3, right? C1 value is equal to 3. And so each isovalue line has the form of C1 x1 plus 5x2 equals constant, right? Or it's going to be x2 equals negative C1 over 5 times x1 plus constant. So, right? So each isovalue line has a slope of negative C1 over 5. Is that correct? Okay, so suppose we change the value of C1 so that the isovalue line becomes steeper than the plant number 3 constraint. So this is the plant number 3 constraint, right? So this is the plant number 3 constraint. Change the color. You know, this is the plant number 3 constraint. Then what happened to the optimal solution? Does the optimal solution remains the same or does it change? So let's see what happened to that. So now the isovalue line becomes steeper than the plant number 3 constraint. Is that right? Then again, let me ask you, is the optimal solution remains the same as before? Or does it has to be changed? If the slope of the isovalue line is steeper than the plant number 3 constraint, it's clearly seen that here, there's more room for us to improve the objective function value, right? So in this case, if we move the isovalue line to this direction, right? This direction. Then we can find the last isovalue line intersecting the feasible reason, right? Which is this. And the new optimal point appears right here, where the isovalue line intersecting the feasible reason. So we may conclude that if a change in C1 causes the isovalue lines to be steeper than the plant number 3 constraint, then the optimal point will be changed from point B to point A. Is that right? So we know that the unit profit for each door is C1. The slope of each isovalue line will be negative C1 over 5. And the slope of the plant number 3 constraint is negative 3/2. So if the isovalue line becomes steeper than the plant number 3 constraint, in other words, or using the mathematical notation, so if negative C1 over 5, that is the slope of the isovalue line, right? So less than negative 3/2. That's the slope of the plant number 3 constraint, right? So if you multiply negative 5 on both sides, that's going to be same as C1 is greater than 15 over 2, which is equal to 7.5. Is that right? So wait, let me change the color. So if C1 is greater than 7.5 here, which is equal to 15 over 2, right? Under this condition, the current basis will no longer be optimal. And the point A, in this case, becomes a new optimal point, okay? If this is true, then, okay. And earlier, I showed you how to get this price and range information from Lindo or Lingo, right? So both Lindo and Lingo provides the objective coefficient ranges by which the objective coefficient can be increased or decreased without causing a change in the basis. And the current value of C1 is 3, right? And here, 4.5 means that the coefficient of variable x, x1, can be increased by this amount, okay? Without causing a change in the basis. So if C1 becomes greater than the 3, that is the current value, right? Current value, which is 3 here, plus 4.5. That is the allowable increase limit, right? So how much is that? 7.5. If C1 becomes greater than 7.5, then the current basis will no longer be optimal. And we've known this already, right? The previous screen, we already identified this, right? If C1 becomes greater than 7.5, then the current basis no longer be optimal. Okay, now let's see how to get this allowable decrease limit of 3, okay, for x1 variable. Okay, so now if the value of C1 becomes smaller and smaller, so eventually, if the slope of the isovalue line changes from negative to positive, like this, what happened to the optimal solution then? Does the optimal solution remains the same? So as the slope changes from negative to positive, this isovalue line is not intersecting the feasible region anymore, right? So we have to move the isovalue line to this direction. Right? It has to move to this direction. Right? And now we know the new optimal point appears right here, point C, right? Where the isovalue line touching the feasible region. So we may say that if a change in C1 value causes the slope of the isovalue lines becomes positive, then the optimal point will change from point B to point C in this case. And the slope of the plant number 2 constraint is 0, right? So if the slope of the isovalue line is greater than 0, that is, if negative C1 over 5 is greater than 0. So if I multiply negative 5 on both sides, then this condition will be same as C1 is less than 0, right? So if the slope of the isovalue line is less than 0, then the current basis is no longer be optimal. And the point C becomes a new optimal point, okay? That's what I can say. And Lindo also provides the same information. So here, the current value of C1 is 3, right? And here, the allowable decrease limit of 3 indicates that the coefficient of variable x1 can be decreased by this amount without causing a change in the basis. Okay, so if C1 becomes less than 3 from the current value, minus 3. Allowable decrease limit, right? Which is 0. So if C1 is less than 0, then the current basis will no longer be optimal. And we've known this information already, right? Right here. Okay. So in summary, oh, sorry. So in summary, this is the these are the allowable ranges to stay optimal for C sub 1. So within these ranges, the window glass should still manufacture 2 glass doors and 6 windows. Okay, so this reason defines the range in which the objective function coefficients can vary without changing the optimal solution. Okay. And of course, Lindo and Lingo provides us these allowable ranges to stay optimal for C sub 1. So that's going to be C sub 1 has to be greater than equal to 3, that's the current value, minus 3, that's the allowable decrease limit, which is equal to 0, right? And then less than equal to, again, 3 from the current value plus allowable increase limit of 4.5, which is equal to 7.5, right? So within these ranges, window glass has to manufacture 2 glass doors and 6 windows. That's how we can interpret this Lingo output. Okay. And of course, even within these ranges, window glass profit will be changed, right? So for example, if C1 value becomes 7, so instead of 3, if C1 becomes 7, then the window glass profit will be 7 times x1, which is 2, right? Plus 5 times x2, which is 6. So how much is that? 44, right? So if C1 value becomes 7, which is still within these allowable ranges, right? Then the window glass profit will be $44 instead of $36, right? But the point is, within these ranges, window glass has to produce the door glass this much and windows this much. Okay. Excuse me. Okay, so just I just want to emphasize this. The Lingo provides the objective coefficient ranges, and within these ranges, the objective coefficient can vary without changing the current optimal solution. Okay. Okay, now let's talk about the effect of a change in a right-hand side value on the optimal solution. Okay, so the here's what you're going to do. So if you change the right-hand side value of the plant number 1 constraint, for example, then this line, that's the plant number 1 constraint, right? So this line will move either way, this side or this side, right? Of course, the feasible reason will change it, right? And if you change the right-hand side value of plant number 2 constraint, then this line will move either way, either this way or this way. So in that case, the feasible reason will also be changed, right? Likewise, if you change the right-hand side value of the plant number 3 constraint, then in that case, this line will move either this way or this way, right? So if you change the right-hand side value of a constraint, the feasible reason may or may not change, and perhaps cause a change in the optimal solution to the problem. So let's investigate on this. Okay, so again, let's use a graphical analysis to investigate this. We are going to determine whether a change in the right-hand side value of a constraint will make the current optimal solution infeasible. So here, let's say B1 is the available production time at plant number 1. And the current value of B1 is 4. Now we will see for what ranges of the B1 value, the current basis remains feasible. So we see that changing the value of B1 shifts the plant number 1 constraint parallel to its current position, right? And we know the current optimal solution, which is point B, is where the plant number 2 and plant number 3 constraints are binding, right? So at this current optimal point, plant number 2 constraint, which is this constraint, and plant number 3 constraint, which is this constraint. These two constraints are intersect. These two constraints are binding at the current optimal point. So if we change the value of B1, then as long as the point where the plants number 2 and number 3 constraints are binding remains feasible, the optimal solution will still occur right here. Okay, where the plants number 2 and 3 constraints are intersect. Okay. So if the value of B1 is decreased to 3 in this case, we still have the same optimal solution at point B, right? And at point B, plant number 2 constraint and plant number 3 constraints are still binding, right? At the optimal point. If the value of B1 is decreased to 2, our current optimal solution still remains feasible. However, this is the minimum value that B1 could take, right? Number 2, the value of 2. That's the minimum value that B1 could take. If B1 becomes smaller than 2, what happens? The plant number 2 and number 3 constraints will be binding in the infeasible region. So for example, if the value of B1 is decreased to 1, decreased to 1, what happened? Do we have the same optimal solution? No. As you can see here, for B1 is less than 2. The plant number 2 and plant number 3 constraints are binding at an infeasible point, right? In this case, the current optimal point is no longer be feasible. Which means the original basis is no longer be feasible, okay? And Lingo output, the right-hand side ranges for each row are the amount by which the right-hand side value can be changed, while the current optimal solution remains feasible. In other words, within these ranges, we still have the same set of binding constraints. So the allowable decrease in the right-hand side ranges for each row or the amount with this amount, the right-hand side value can be decreased without changing the binding constraints, okay? So the current value of B1 is 4. And here the value 2 means B1 can be decreased by this amount without causing an infeasibility of the current optimal solution. Okay, so if the right-hand side value for row number 2, which is B1, becomes less than 4 That's the current value minus 2. Allowable decrease limit, which is equal to 2. If B1 is less than 2, then the current optimal solution becomes infeasible. Okay? Then the current optimal solution becomes infeasible. Okay. Okay, now let's see why we have infinity as the allowable increase limit. Okay. So currently the value of B1 is 4, right? So if we increase the value of B1 to 5, of course, the feasible reason has been expanded. However, it doesn't impact on our optimal solution, right? So optimal solution remains the same at point B, where the plants number 2 and plant number 3 constraints are binding, right? If the value of B1 is increased to 6, right here, right? Then we still have the same optimal solution occurs at point B, right here, where the plant number 2 and plant number 3 constraints are binding. If B1 becomes 7, then the plant number 1 constraint becomes redundant constraint, right? And it doesn't impact on our optimal solution. So what can you say from these results? Increasing the value of B1 doesn't impact on the current optimal solution, right? We still have the same optimal solution at point B, where the plant number 2 and number 3 constraints are binding, right? Yeah. So we have infinity as the allowable increase limit of B1. Okay. Again, within these ranges, the current optimal solution remains feasible, and the current set of binding constraints remains the same. Okay. And so as long as the value of B1 greater than or equal to 2, according to the Lingo and Lindo output here. So I'm talking about this one. So as long as B1 value is greater than equal to 2 from here, right? The current optimal solution remains feasible. And the current set of binding constraints also remains the same. Okay. Okay, then let's try one more. So for the ranges of right-hand side value in the plant number three constraints. So now I'm talking about B3, okay? So the current value of B3 is 18, right? So, okay, oh, okay, down here, I already provided you this. Okay, that's the plan number 3 constraint. And that can be rewritten as this, right? So plan number constraint has the slope of -3/2, and it has x2 intercept of 18/2, which is equal to 9, right? So this line, plan number 3 constraint, hits the value of 9 up here. That cross this point. Okay. Okay, so let's see for what range of B3 values the current basis remains feasible. So just like the case of B1, changing in B3 moves the shifts the plan number 3 constraint parallel to its current position, right? So currently B3 is 18. So if B3 is decreased to 14, what happened then? In that case, the x2 intercept of the plan number 3 constraint becomes 14/2 instead of 18/2, right? This is going to be equal to 7, right? Which is right here, right? So x2 intercept of the plan number 3 constraint becomes 7. And the point is the plan number 2 and plan number 3 constraints are still binding in the feasible region. Is that right? If B3 is decreased to 12, then the x2 intercept of the plan number 3 constraint becomes 12/2, which is equal to 6 right here, okay? And the important thing is plan number 2 and plan number 3 constraints are still binding in the feasible region, right? However, this is going to be the smallest value that B3 could take. If B3 becomes smaller than 12, then you can imagine that the plan numbers 2 and plan number 3 constraint will be binding at an infeasible point. See here? So for example, if B3 is decreased to 10, which is less than 12, the plan number 2 and plan number 3 constraints are binding in the infeasible region. So the allowable decrease limit to stay feasible for B3 would be this, right? B3 has to greater than, B3 has to be greater than or equal to 12, okay? That's the allowable decrease limit to stay feasible. For the right-hand side value in the plan number 3 constraint, okay? Okay, then how about the allowable increase limit to stay feasible for B3? So current value of B3 is 18. Now if B3 is increased to 21, then the plan number 2 and plan number 3 constraints are still binding in the feasible region, right? If B3 is increased to 24, the plan number 2 and plan number 3 constraints are still binding. Right? These two constraints are still binding in the feasible region. And we know that this is the largest value that B3 could take. If B3 becomes larger than 24, then the plan number 2 and plan number 3 constraints will be binding in the infeasible region. See here? So in this case, if B3 is increased to 27, which is greater than 24, then the plan number 2 and plan number 3 constraints are binding at the infeasible point. Because in this case, the plan number 1 constraint for doors is not satisfied, okay? So in this case, the current basis will no longer be feasible. So the allowable increase limit to stay feasible for B3 would be less than or equal to 24. Okay. Okay, so according to Lindo and Lingo output, the current value of B3 is 18, right? And the allowable increase limit is 6, and allowable decrease limit is also 6. So B3 is less than or equal to and greater than or equal to 18 plus 6, 18 minus 6, right? Which is 12 and 24. So these are the allowable limit, okay? Allowable ranges for B3. So within these ranges, the current optimal solution remains feasible. and the current set of binding constraints also remains the same as before. Okay. Okay, so this is all for today. And next time, we're gonna continue to talk about the sensitivity analysis. And next time, I'm gonna introduce the concept of dual price and how it can be used for our sensitivity analysis. Okay, thank you. Bye-bye.